Today, we're going to actually continue talking about what we started last time, which was this idea of payment channels and using scripts to do more interesting things. So last time we saw what we call a one-way payment channel. And the idea here was that Alice wants to pay Bob, but maybe she wants to pay Bob many times. So our example was the example of a mobile network, and Alice wanted to just pay for making a call. And we saw that instead of creating a large number of transactions on chain, instead of creating a large number of Bitcoin transactions and having to pay transaction fees for all of them and having to wait for all of them to get on chain, we had a completely different solution. And the solution was that first, Alice creates a transaction where she puts a deposit. So this was transaction 1. And let's say this was 100 Hong Kong dollars. And this was an input that belonged to Alice. And then originally Alice said that I want to lock this so that in order to use this output, which is also 100 Hong Kong dollars, one of these two conditions must happen. So either you need to provide signatures from both Alice and Bob, or you should just provide a signature from Alice, but the time should be after some predetermined deadline. Signature from Alice. And my time or my block number should be more than some number t. Okay. So this was the deposit transaction. And we said that in step 1, Alice publishes this transaction. So now her money is locked, and the only way she can get back this money is if she convinces Bob to sign something, or if time passes and we are going to be after time t. And here the idea is that we want Alice to be able to pay Bob until time t, or actually to be more specific, until a while before t, because we want to also consider what happens if the transactions need confirmations and things like that. So my timeline looks something like this. So this is the time that transaction 1 was published. And let's say this is the period in which Alice wants to pay Bob. So I should be able to support payments from Alice to Bob here. And then let's say this is t. So there is a time much after the last payment from Alice has to go to Bob, where Alice can take her money back if Bob does not use it. And then we saw the idea that if Alice wants to pay Bob, she doesn't actually pay Bob on chain. She doesn't actually create new transactions and publish them. She just creates transactions and gives those transactions to Bob. And this was the idea. So Alice creates a series of transactions. So we said that in the first minute, she creates a transaction that looks like this. It uses the 100 Hong Kong dollars that were here. So this input, sorry, that output as its input. And let's say it pays 1 Hong Kong dollar to Bob and 99 to Alice. Okay. Now let's call this one Okay, maybe it would have been better if I called this one transaction 0. So let's call that one transaction 0. Okay. So transaction 0 is the transaction that is putting in the deposit. And let's say this is transaction 1. This is a transaction that is paying 1 unit to Bob and 99 units back to Alice. So Alice creates this and she signs this transaction and sends it to Bob. Okay. So Alice creates and signs transaction 1. But doesn't actually publish it on the network because, of course, it would be an invalid transaction because this transaction is using these coins here, this output of transaction 0. And in order to use this output of transaction 0, you need signatures from both Alice and Bob. So Alice creates and signs this transaction 1 and sends it to Bob. Okay. Now, the idea here is that if Bob wants to reclaim the money, he can just sign this transaction 1 and publish it. And since this transaction 1 just needs signatures from Alice and Bob, and since Alice has already signed it and sent it to Bob, now Bob can reclaim the money. So the only person here who can actually do something on-chain is Bob. Only Bob can sign this transaction and publish it and make it so that this money is used. Now, we said that in the next unit of time, let's say Alice wants to now pay Bob instead of 1, Alice wants to pay Bob 2 units. So Alice creates another transaction, this time giving 2 to Bob and 99 back to herself. Sorry, 98. Back to herself. And this is also going to use the exact same coin as its input. Okay. And again, of course, these transactions are going to have transaction fees too. I'm not considering the transaction fees. Okay. So maybe if I want to also add the transaction fees, I can say that this deposit here was not 100, it was, let's say, 101. Right? So this ensures that I'm using 101 as input and I have the sum of my outputs equal to 100. So 1 unit is going to be paid as a transaction fee. Let's say. Now, okay. So again, Alice can create this transaction too, just as before. She can sign it and she can send it to Bob. Now, at this point, Bob has both of these transactions and can sign any one of them and publish it on the network and then get his money. But of course, Bob would prefer to sign transaction 2. It would be stupid for Bob to just sign transaction 1 since he's paid less there, right? And he cannot sign and publish both of them. I mean, he can, but if he does that, then that's double spending. And at most, one of these 2 transactions will end up in the blockchain because they're both using this particular output coin here. So we're sure that Bob cannot get more than the 2 units that he was promised in transaction 2. Okay, and then we can just continue this. And we said that, let's say I have K transactions. Transaction K can be that Alice pays K units to Bob and 100 minus K units back to herself. Again, using the exact same input. And yeah, just as before, Alice just creates all of these transactions, signs them, and sends them to Bob. Okay. Now, we have several properties here. And by the way, remember from last time why we had this extra condition at the end? The extra condition was so that if Bob refuses to publish any of these transactions, if Bob wants to extort Alice and says, oh, I don't want to publish any of these transactions, then Alice can just wait until after time T and she can take all of her money back. So the reason I had this part here, this is called actually a time lock, because I'm locking the money until after time T. The reason I had the time lock here was to make sure Bob has to publish one of these transactions. And of course, if Bob has to publish one of these transactions, Bob is rational. Bob wants to maximize the amount of money that he gets, so he publishes the last one. So we can say that the next step is that when all the transactions are done, Bob publishes, okay, well, I forgot the signature. Bob signs transaction K and publishes this transaction on the blockchain. So we publish it on the network, it will eventually get on the blockchain. Okay, great. Now, something's wrong with my chair. Okay, this is what we have, and we had this in the last session as well. But what are the properties of this channel? So whenever I talk about a payment channel, this entire protocol is what I'm talking about. Well, first of all, this is a one-way channel, right? Only Alice can pay Bob. There's no way here for Bob to pay Alice. And secondly, it has a limit on the time. So I can use it at most in this particular time segment. I cannot use this channel after time T, because if the time passes T, then, well, Alice can get all of her money. So Bob would never let this happen. So Bob would definitely publish one of these transactions before time T. And also the other thing here is that Bob can close the channel at any time. Right, so if I want to make, let's say I'm Alice, I want to make 1,000 transactions. Maybe I've made 100 transactions and Bob just wants to close the channel. He can just publish the transaction 100 that is already given to him, and he can close the channel. So these are basically the properties we have, and we want to see how we can relax these and how we can make stuff better. So again, money flows only from Alice to Bob. So it flows only in one direction. And Bob can close the channel. And we have an expiry date, basically. We say that the channel expires at time T, which is a time that we have set before. And of course, there is a limit on how much money can be transferred. So Alice cannot transfer in this channel more than her original deposit, minus transaction fees. So there is also a limit on the amount of money, and we call that the capacity of the channel. So the channel has a limited capacity. Actually, let's call it a fixed capacity. Okay, some of these are desirable properties. So I might want to have, for example, this property that Bob can close the channel at any time. I would like to have this one, which says that the channel expires. I don't want to have a channel forever. But some of them are not so great. For example, today we will talk about this problem here, that money flows only in one direction. But the most important thing here is that even though I'm creating a lot of transactions, all of these transactions are what we call off-chain. And by off-chain, I mean that they are just transactions that are being sent from Alice to Bob. So only Alice and Bob are seeing these transactions. These transactions never actually make it onto a blockchain. The only two transactions that are actually mined and added on the blockchain are the first transaction. So when Alice is putting down the deposit, that has to be on-chain. And the very last transaction. So when Bob publishes the last transaction to get his money, that's something that gets added on the blockchain, right? So that's a huge positive. It's that only two transactions are added to the blockchain. And what this effectively means is that we only pay transaction fees twice. And that's, of course, amazing because we can make as many transactions in a sense as we like. It's not really a transaction, but I can make as many payments as I like, right? So, and I don't necessarily have to pay in units of one either. So if I'm Alice, I can just keep paying Bob. And every time, as long as I'm increasing the amount that I'm paying to Bob, this entire protocol would work. So only two transactions are added to the blockchain, which means only two transaction fees have to be paid. Whereas I can have as many payments as I like from Alice to Bob. So I had K payments, and K can be any number really. So even though I'm making K payments, I'm only paying two transaction fees. I'm not paying transaction fees for all of them. But there is also a much more important point here. When we were making transactions on the blockchain, we talked about this several times, that if you see a transaction, it doesn't mean the transaction is finalized. You have to wait for that transaction to get on the blockchain. And even then, there might be a fork, and then this transaction might be reverted. It might be removed from the consensus chain. So we had to wait for confirmations. We had to wait for blocks to come after the block that contained our transaction. But we have none of that here, right? If I want a payment from Alice to Bob, that payment is instant, because Alice can just create this transaction, whatever. Let's say I want to have another transaction K plus 1. Alice can just create that transaction on her own machine really fast, and then she can sign it and she can send it to Bob, and that's it. That's the end of the payment, right? Because we are sure that Bob can settle that payment later on. We're sure that Bob can finally, at the end of the entire time frame here, publish the last transaction and get his money. So in a sense, now we have instant payments, which is another huge point. I'm going to add it at the end of this page. Payments are instant. Of course, they're instant within the limits of the channel, so I cannot send more money that I have put in here. But this is amazing. So now Alice can pay Bob instantly, even though we are using a blockchain where transactions take, let's say, 1 hour to get finalized and get the confirmations and everything. And the entire reason for that is that I don't have to wait for confirmations here. I can just, as Alice, I can just send this transaction to Bob. And since I've already deposited the money sometime in the past, Bob is sure that he can always settle these payments. Bob can put the very last transaction on the blockchain at any time and get his money back. Of course, when he puts the last transaction on the blockchain, he has to wait for confirmations and so on. And that's why I'm saying that the payments from Alice to Bob cannot go all the way to time t. They have to be up until some smaller time here. And then this part, this is where Bob has published the last transaction, and he's now waiting for confirmations on this last transaction. Okay. Now, these are all great, but the main problem I have is this one. I don't like this one. My money can only flow in one direction. So I have only a one-way payment channel. I'd like to have a two-way payment channel. Because here's the thing. So let's consider kind of a different scenario. Let's say that Alice and Bob are friends, and they have to transfer a lot of money between themselves. They have a lot of transfers. Maybe they need to make a long list of transfers every day. So whatever, they want to transfer 100 times between them every day. And also, they don't want to pay transaction fees for each one of these. So they want to create a channel between themselves. But the payments are not just one way. The payments are two-way. So it might be that Alice wants to pay Bob, and it might also be that Bob wants to pay Alice. Now, the simplest solution that comes to mind, and this is not actually a great solution, but let's just go through it, is this. So my simple solution is to create two one-way channels. So create two one-way channels, one from Alice to Bob and one from Bob to Alice. Okay. So I have a channel from Alice to Bob and another channel from Bob to Alice. Now, what's the problem with this? The problem is that if you look at this one-way payment channel, Alice could only ever increase the amount that she's paying to Bob, right? So if I'm paying 1 unit to Bob, I can later decide that now I want to pay 2 units to Bob. But I cannot decrease the amount that I'm paying to Bob. Because if I've already signed a transaction that gives K units to Bob, and then later on I want to change my mind and say I want to only give K minus 1 units to Bob, Bob will always have the option of publishing the transaction that's paying the most to him, right? And then he will get that amount of money. So in my one-way payment channel, the amount of the payment can only increase. And this is, again, part of this concept that the money flows only in one direction. So Alice can only increase the total payments to Bob. But also, I have a limit on how much I can pay, right? So in this case, let's say if I want to pay $1 for the transaction fee, then I can pay at most $100 to Bob. So I would say that this is a channel with a capacity of 100 in this case. Okay. Now, here's the problem. If I have a one-way channel with capacity, let's say 100 from Alice to Bob, and I also have a one-way channel with capacity 100 from Bob to Alice. Now, consider this sequence of payments. Let's say that Alice pays Bob 99, or okay, not even 99, let's say 75 Hong Kong dollars. Okay. Now I have two channels. This is my channel 1, which is the channel Alice uses to pay Bob. And let's say this is channel 2, which is the channel that Bob uses to pay Alice. So if Alice pays Bob 75 Hong Kong dollars, she's paying this on channel 1. Okay. And then let's say that Bob wants to also pay Alice $75 later on. So Bob pays Alice $75. But of course, Bob is using channel 2. We have two completely separate channels. Okay. He's paying this on channel 2. Now let's say that Alice wants to pay Bob 70 or this time, whatever, some number. Alice pays Bob 50 Hong Kong dollars. This payment cannot go through. Why is that? Well, my channels had a capacity of 100 at the beginning. So when Alice pays Bob 75 Hong Kong dollars on channel 1, then channel 1's remaining capacity is only 25. Right? And by this, I mean that Alice can pay at most $25 more to Bob using channel 1. And the same thing happens here. So when Bob pays Alice 75 Hong Kong dollars on channel 2, channel 2's remaining capacity is going to reduce. Okay, but now at this point, when Alice wants to pay Bob, we have a problem. Alice can only pay Bob using channel 1. And channel 1 has a capacity of 25. So not enough capacity in channel 1, and Alice cannot pay Bob. Of course, she can create another channel, but we have to create another channel from Alice to Bob. So the point here is that if I have two one-way channels, it's not the same as really having a two-way channel where both Bob and Alice can send and receive money, right? Because if you think about it, if these channels worked like bank accounts, if Alice pays Bob 75 Hong Kong dollars, then Bob has that money in his bank account and he can pay Alice back 75 Hong Kong dollars, and then Alice has that 75 and she can pay Bob. But this is not how things are working here. We have two channels and every channel has a limited capacity. So the total amount that can go from Alice to Bob is at most 100. And the total amount that can go from Bob to Alice is also at most 100. It does not matter. They don't cancel each other out. So it's not just that the balance between Alice and Bob should be in some predetermined interval. It's that the sum of all the payments from Alice to Bob should be at most 100. And the sum of all the payments from Bob to Alice should be at most 100. So this is not ideal. That's why I would like to create a two-way payment channel. And to create a two-way payment channel, basically, I want to take my one-way payment channel and I want to make it so that money can flow in both directions. Okay? Because if I can create that, then hopefully I can turn it into a functioning two-way channel. Okay? So this is our second attempt. So this simple solution doesn't really work. Let's try this second attempt. And let's say I want to have, again, let's just keep the one-way channel here. But let's say that I want to relax this condition. I want to have a situation where money can flow in both directions. Okay. Let money flow in both directions. Okay, so let's say that I have the same deposit transaction as before. Let's say I have this transaction 0, and here Alice was paying 101. And we had an output, and the condition to use this output was to have either a signature from Alice and also from Bob, or to just have a signature from Alice and the time is more than some amount. So, and my time is more than t. Okay, and now here's the thing. As I create the transactions just like before, as I create this transaction 1 to K, I saw that I can increase my my payment to Bob. So let's say this is transaction 1. It is paying 1 unit to Bob and 99 to Alice. And this is coming from here. And then let's say I have another transaction. And this time, let's say I'm paying 10 units to Bob and 90 units to Alice. And this is also coming from here. And just as before, Alice is just creating these transactions, but not publishing them. Alice is only giving these transactions to Bob. And let's say I have a bunch of transactions like this, but let's say now I want to decrease the amount of the payment. So this is effectively the same as saying Bob is paying Alice. So let's say that Bob wants to pay Alice 5 units back. So in this case, Alice needs to create another transaction. Let's call this one transaction 3. And this pays 5 units to Bob and 95 units back to Alice. And it uses, again, the same coin as its input. Okay. Now, if Alice just signs this last transaction and sends it to Bob, that's actually not enough, because now we're trusting that Bob would actually be honest and would only publish this last transaction, whereas Bob can publish transaction 2 and actually make more money. And if you've learned one thing in this course, it's that we never trust anyone. So Alice would not be willing to accept this payment from Bob. So, or maybe instead of a payment, let's talk about a refund. So let's say by the end of transaction 2, at the time that Alice has given transaction 2 to Bob, she has paid 10 units to Bob. And now let's say that Bob wants to refund 5 units to Alice, right? So if Alice creates this transaction 3 and sends it to Bob, that's not really a refund, because Bob can still claim these 10 units from here. So that's a problem. Now, how can we make sure that this cannot happen? How can I make sure that Bob cannot publish one of the old transactions? So the entire idea here is that I want to make sure that if Bob published any transaction other than the last transaction, he will actually be punished, or he will lose a lot of money. Okay. So here's the idea. Previously, we had added this thing. Sorry, it's not very easy to read. So this was signature from Alice, and time is more than T. So remember, we added this time lock because we didn't trust Bob. And we were thinking, okay, if Bob doesn't publish any of the transactions, then we should be able to punish Bob and give all the money to Alice. So if Bob doesn't publish any of the transactions by time T, then Alice can just use all of the money and give it back to herself, right? But here, I have kind of a similar situation, but not exactly the same. So I want to say that if Bob does something dishonest again, then Alice can use the entire money. So what I'm going to do here is that I'm saying in transaction 1, transaction 2, and transaction 3, instead of actually paying Bob, I don't really pay Bob. I create another condition here. And the condition here is this. It says you can use this money if you have a signature from Bob, and instead of signature from Bob, I'm just going to write Bob. Okay. You can use this money if you're Bob and the time is after some limit, let's call that T. Or you can use this coin if you're Alice and you can prove that Bob has cheated. Okay, Alice and let's say Bob, oh, this is really hard to fit, cheated. Okay, I'm going to write just C, and by C, I mean a proof that Bob has cheated. Okay, so the idea here is that if Bob publishes one of the old transactions, he's not going to just get the money. He will only get the money after time passes and goes after this time T. But while the time is before T, Alice can actually go ahead and prove that Bob has cheated and take all the money that Bob had here. And I will use the same conditions in all of my transactions. Okay. So all of these will change to signature from Bob and time is after T, or signature from Alice and a proof C. Okay, and this is the same, Bob and time is greater than T, or signature from Alice. Oh, I just realized I'm not consistent with my notation. That's fine. Okay. So basically what we're doing here is that in transaction 0, Alice is putting down some money as deposit. This is 101 units. And then in each one of these transactions, previously she was like, I'm going to pay Bob 1 unit of money, or I'm going to pay Bob 2 units. And of course, this transaction would only be valid when it has Bob's signature because it's using this output. Now here, instead of just saying, I'm paying Bob 1 unit, Alice is saying, Bob can claim this 1 unit if the time is after T. But if I can prove that Bob has cheated, then I can claim this 1 unit of money. Okay, so she creates a transaction that has these conditions in it. She signs this transaction TX1 and sends it to Bob. Now, of course, TX1 is using this output, so it needs Bob's signature to be valid. So Bob can sign TX1 and publish it at any time. And the same thing happens with transaction 2, TX2, and TX3 here. But if Bob publishes one of these transactions, he's not going to immediately be able to use his money. He has to wait until time T. And in that period, Alice has a chance to prove that Bob has cheated. And if she can prove that Bob has indeed cheated, then she can take all the money, because this part of the money is already given to Alice, and this part, Alice can take it if she can prove that Bob has cheated. So this is the general idea of how this protocol is supposed to work. But now the question is, of course, how do I create proofs like this? So let's say Bob has actually cheated. How can I prove that? Well, what does it mean to say that Bob has cheated? If we want to be very specific here, what is the cheating that I'm talking about? I mean that Bob has published some transaction that was not the last transaction. So he published transaction I, but there is a transaction J, where J is greater than I. Okay. So there's a question in the chat. Do the output to Alice in transaction 1, 2 to K have the same conditions as transaction 0? No. So here, when I'm saying Alice, it means that you can use this coin if you have a signature from Alice. So Alice can definitely use these coins here. Whereas here, you had this entire condition. right? So basically transaction 0 is locking Alice's funds. And then in each one of these transactions, Alice is saying, for example, in transaction 2, Alice is saying, I'm willing to pay Bob 10 units, assuming that Bob does not cheat, right? So Bob can claim these 10 units if the time has passed T, and I, as Alice, have not proven that he has cheated, right? But this part, this one doesn't have a condition. This one goes directly to Alice. But of course, it's Bob who decides which one of these transactions to publish. Okay, so what is how can Bob cheat? What do I mean when I say Bob has cheated? I mean that Bob has published one of these transactions, but there was actually a transaction with a higher number. So for example, here, if I have 3 transactions, if Bob publishes transaction 2, he has cheated because there was a transaction 3. Okay. So another question in the chat. So the channel will run out of money once Alice paid Bob. It's not very well defined what you mean by the channel runs out of money. So Alice can pay up to 100 units to Bob here, right? And the way she does that is that for every payment, she creates a new transaction. So I think what you mean there is what I call Bob closing the channel. So Bob can publish any of these transactions on the blockchain, and as soon as he does that, that's the end of the lifetime of the channel, right? So then Alice will not make any more transfers of money in this channel. So the channel is the entirety of this thing, like all of these things, and this initial transaction and all of these transactions, they're all called a channel because they're a way for Alice to pay money to Bob. Okay. But how can I prove if Bob cheats? How can I prove if Bob publishes transaction 3? Now, I first want you to consider that Bob would only cheat if it actually pays him more money, right? So if I didn't have this last transaction, if I only had transaction 1 and transaction 2, transaction 2 is the one that is paying the most amount to Bob. So Bob would never publish transaction 1. That's just stupid. Like, he will lose money. He will just get 1 unit instead of 10 units, right? So I don't want to really guard against that. I want to guard against the case where I have 3 transactions like this, for example, and the last transaction is actually not the maximum payment to Bob. And then Bob is going here in the list and finding the transaction that is paying him the maximum amount and publishing that instead. So I want to basically guard against this. And remember, this only happens when Bob wants to give a refund. So at the time of transaction 2, Alice was paying a total of 10 units to Bob, and then we said Bob wants to refund 5 units of this to Alice. Right? So basically, when I'm saying that Bob has cheated, I mean that Bob is not honoring some of the refunds that he owes to Alice. Okay. So it's not just that Bob is publishing transaction I and there is a larger transaction, a transaction with a larger index, but it's also that transaction I is paying Bob more than transaction J. So when I say Bob cheated, I mean Bob has published transaction I, but there is a transaction J with J larger than I that pays Bob less than transaction I, that pays less money to Bob. So this is now my definition of cheating. Okay. How can I prove this? Well, first of all, I can just if I'm Alice, I can just include one extra piece of information in every transaction, and that's the number of that transaction. So I would include the number 1 in this transaction, saying that this is transaction number 1. I would include 2 here, or I would include 3 here. Instead of a number, I can have a timestamp. So I just want to have a way of saying when this transaction happened, and did this transaction happen before this other one or after one? Okay. So here's the thing. Alice can ask Bob to give a signature on the index or the timestamp of every transaction. So this is how we edit our protocol. The change in protocol is this. Bob has to sign the index of every transaction. And as I said before, instead of an index, I can use a timestamp. So what does this mean? It means that if I'm Alice, I first create transaction 1 and I sign it, I send it to Bob. Now Bob has to give me a signature that basically verifies that he has received transaction 1, that he believes that one transaction has taken place. Then I sign and create another transaction, transaction 2, send it to Bob. Bob has to give me confirmation. Bob has to send me a signature on the number 2, saying that transaction 2 is now signed. Of course, these numbers will not just be numbers, they will be timestamps in the real world, but again, I'm using numbers here. Now, when I sent transaction 3 to Bob, this is actually at the request of Bob. So Bob is telling Alice, hey, I want to give you 5 units back. I want to refund you 5 units. And then Alice just creates a new transaction, puts the index here, sends it to Bob, and of course, signed by Alice. And then Bob has to sign the index of this transaction and send that signature back to Alice. If Bob does not do that, that's effectively the same as saying that the refund has not happened. Of course, the refund cannot happen if Bob doesn't want to give a refund. We want all the payments to be consensual. So if Bob actually wants to give a refund, the way that he does give the refund is that he signs the index of this transaction. Now, the proof that Bob has cheated, if Bob later publishes transaction 2, Alice can just use Bob's signature on the index of transaction 3. So here, this C would actually check if Alice can provide Bob's signature on an index that is larger than the index of the current transaction. Then this shows that Bob has cheated. It shows that this was not the last transaction, and then Alice can get the entire money. Okay? So our proof C is just going to be Bob's signature on the index of a transaction okay, let's do it something like this, on an index larger than current transactions index. If Alice can provide this, she can get them. Okay, so let's just review everything one more time. So this is now our one-way channel with refunds. So, sorry, my first step is that Alice puts down a deposit. And as we saw before, this is the way it works. So Alice puts some money, let's say 101 here, and the condition here for spending this money is the same as what we had up here in our original one-way payment. So either providing signatures from both parties or a signature from Alice, and the time is after T. Okay. So here I just say, okay, where do I put this? Not enough space. Let's say I create this one. This is transaction 0. It has an input from Alice and it has an output. And the condition of using this output is that you either provide a signature from Alice and a signature from Bob. That's what I mean when I'm writing it like this. Or you provide a signature from Alice and the time is more than some T. Okay. Now, if I want to increase the payment, so when Alice wants to pay Bob, she's just going to create new transactions and sign them and send them to Bob. This is exactly as before. So Alice would create a transaction. She would use this output as the input to her transaction. And then let's say she pays 1 unit here and the rest 99 back to herself. So I'm going to call this condition here. I'm just going to put a star. I will write what the condition star is. And this is transaction 1. So when Alice wants to pay Bob, the first step is that Alice creates this transaction. Now, in this case, I'm calling it transaction 1, but it can be transaction K, the newest transaction, where this condition is actually a little bit more complicated. So the idea here is that Alice is saying, if Bob signs this transaction and publishes it, then he should be able to get this money as long as I cannot prove that he has cheated. Okay, so this star, the condition for accessing this piece of money, this 1 unit here, is that either you have a signature from Bob, so Bob is trying to spend it, and the time is more than T, so we're after time T and Bob is trying to spend it, or Alice is trying to get it by proving that Bob has cheated, and Alice can provide a signature of Bob on some number J that has to be larger than 1. Right? Because this was transaction number 1. So if Alice can provide a signature on Bob on a number J that is greater than 1, and of course she has to also provide J itself, then she can prove that there were more than 1 transactions, and Bob, so since Bob has published this transaction on the blockchain, and Alice is proving that Bob published the wrong transaction on the blockchain, Alice can now take all of Bob's money. Okay, but in our protocol, the way it works is that Alice creates this transaction that has this code, this script in this part, and then Alice signs this transaction and sends it to Bob. Oh, and by the way, this has to be K, right? So it wasn't necessarily just my first transaction. Let's say this was the case transaction, and it's not necessarily paying 1 unit to Bob, it's paying something to Bob. So let's say it's paying B units to Bob and it's paying A units to Alice. Now, this is what happens when Alice wants to pay Bob. But what happens when Bob wants to issue a refund? So when Bob wants to refund, so first Bob tells Alice how much he's willing to refund. Okay, so let's say that the last transaction that they've had was this. Let's say the last transaction was transaction K-1, and it was paying some amount B to Bob, of course, using this condition. And it was paying some amount A to Alice. Okay, and all of my transactions use the same input, which is this output of the deposit transaction. Okay, so let's say Bob wants to refund. So the idea is that he was being paid B. Now he wants to be paid some new amount B prime, which is less than B. Bob wants to refund and be paid only B prime that is less than B. So here the first step is that Bob tells Alice. So Bob asks Alice to create a new transaction. So it's always Alice who's creating these transactions. And then in the next step, Alice creates transaction K. Now this transaction is going to have the amount B prime to Bob, and of course some new amount A prime to Alice. So this is paid to Alice, and the amount that is paid to Bob is paid using the same condition. Okay, so using the condition that Bob is not cheating. And this is, again, whenever I'm putting dots here, I mean it comes from up here. Okay, so Alice creates this transaction, signs it, and sends it to Bob. But this is not yet done. So at this point, Alice doesn't believe that she's paid a refund, because of course, Bob can still go back and publish transaction K-1 instead of transaction K. Right, so we have a last step, and the last step is that Bob signs the index K and sends it to Alice, and sends this signature to Alice. Now, why is this so important? Because when Alice receives Bob's signature on this index K, now Alice knows that Bob cannot use any of the transactions that had an index smaller than K. Because if Bob publishes any of the transactions that had an index smaller than K on the blockchain, then that transaction has this condition. And then Alice can just provide Bob's signature on this last transaction and get all the money. Okay, so this last part, part C, is basically Bob's commitment. He's committing that I'm not going to publish any transaction except for this last transaction. And this is how we can have a flow of money in both directions. So now Alice can pay Bob as much as she likes, of course, up to this limit here. And then Bob can refund any amount of this payment. So you see, we're now kind of having a two-sided channel. It's not yet completely a two-sided channel. It's a one-sided channel with refunds, right? But we can use the same idea to have a two-sided channel. How can I have a two-sided channel using the same idea? So let's say I have a one-sided channel with refunds. Tell me in the chat, how can I create a two-sided channel? I want a two-way channel now. Well, I can use the exact same solution that I had here, right? So originally I was just saying I have two one-way channels, but now let's say I have two one-way channels with refunds. Okay, so this is how I can have a two-way channel. I can say that Alice creates a one-way channel C1 to Bob, but this is not just a normal one-way channel, this is a one-way channel with refunds. It can have a refund in. And Bob does the same thing. So Bob creates a one-way channel with refund called C2 from Bob to Alice. Okay. Let me write this one like that as well. So Alice creates C1 from Alice to Bob. And let's say the capacity of this channel is 100 and the capacity of this channel is also 100. Okay. And both of these channels also have this refund capability. So I have these channels with refunds. Now let's consider the same situation as here. So first Alice is paying 75, then Bob is paying Alice, then Alice is again paying Bob. Okay. So let's say these are the payments that I want to have. First, I want Alice to pay 75 to Bob. And then let's say I want Bob to pay 80 to Alice. And then finally, let's say I want Alice to pay 50 to Bob. How can I do this? Well, Alice wants to pay 75 units to Bob. So we can say that this would be a new payment on, or okay, I just say Alice pays using the first channel, using C1. So now I have a situation here where C1's capacity has decreased. So C1's capacity is now only 25. I don't know why I did that. Okay, because Alice has paid 75 units in C1 to Bob, and the original capacity was 100. So now I have a capacity of 25 in C1. Now Bob wants to pay 80 to Alice, but the way he does this is not necessarily only using C2. So he can make part of the payment using a refund on C1. So if Bob wants to pay 80 units to Alice, well, Alice has already paid Bob 75 units in C1. So Bob can refund 75 units in C1 and then pay 5 units in C2. So here I say Bob refunds 75 units in C1, and now C1's capacity is back to 100. Right, because I did a refund. Now Alice can again pay up to 100 units in C1 if she wants. And well, Bob wanted to pay 80 in total. He has refunded 75 in C1, but he also pays another 5 units in C2. And now C2's capacity is 95. Because remember, C2 was a channel from Bob to Alice. Now, if Alice wants to pay 50 units to Bob, well, again, we do the same thing. Alice is already paid 5 units in C2, so she can first refund these 5 units. And after refunding these 5 units, she can pay another 45 units in C1. So here, Alice refunds 5 units in C2, and now C2's capacity is back to 100. And then Alice pays the remaining 45 units in C1. And now C1's capacity is 55. Okay. Now, why is this better than the previous case? Because all of these payments and refunds, all of these are being done off-chain, right? So when they're doing these payments and refunds, they don't have to actually create transactions that go into the blockchain and then wait for them to get confirmations and also pay transaction fees. They have none of that. These are just transactions that are being signed and sent between Alice and Bob. This is an off-chain protocol. Everything is off-chain. And as you see, now I can transfer as much money as I want, as long as I also use the refunds for my transaction. So I don't have this extra constraint that I had before. So before, I had to say that the total amount of money that goes from Alice to Bob should be at most 100. And the total money that goes from Bob to Alice should be at most 100. But now I just say the difference between the amount that is paid from Alice to Bob and from Bob to Alice should be between minus 100 and 100. So you see, I now have a situation where I can have a lot of transactions as long as no side owes the other side more than $100 at any given time. Okay? And I do as many transactions as I want. And then at the end of the day, I just come back and I close my 2 channels. And one of them can be closed by Alice, the other one can be closed by Bob. Of course, I will close all of them before this time T, because my channels also had an expiry time. So now Alice and Bob, let's say if they're friends, they can easily transfer money between themselves, and they can be sure that those transfers will be honored, because at the end of the day, when they close the channels, all of the payments and refunds in that channel have to be honored. So we have a settlement mechanism, but also we don't have to go to the blockchain for every single one of our payments. Now, the small downside here is that we actually use 2 different one-way channels with refunds to create our 2-way channel. So if we go back to our one-way channel, in our one-way channel, the really good thing was that we only needed 2 transactions for a one-way channel. We needed a transaction that funded the channel and basically put down the deposit. And then we needed to publish the very last transaction that would close the channel. But now, since I have 2 channels, I have 4 transactions. Of course, 4 transactions is still not that bad. I would be happy to have 4 transactions. It's a constant number of transactions. So no matter how many payments I want to do, I'm doing only 4 on-chain transactions. But we can get this down to 2. So now I have, this is both a plus and a minus. I have only 4 on-chain transactions, 2 transactions for each channel, for each one-way channel. But yeah, so one of the things that I really want you to think about is if you can come up with a better way of creating a 2-way channel using one-way channels with refunds, so that I don't have to have 4 on-chain transactions. And the hint that I would give you here is that instead of just having one party put all of the deposit, what happens if in the original funding transaction or the deposit transaction, both parties put a deposit? Can we then make the entire thing work so that we only need 2 on-chain transactions instead of the 4 that we're using right now? Okay, so we're almost running out of time. I just want to say one last point here. This is not really a topic that we will cover in this course, but this idea of payment channels like this is the main underlying idea for layer 2 payment protocols. So here's the thing. Suppose that you're a bunch of people who have a lot of transactions between yourselves, not necessarily just 2 people, not necessarily just Alice and Bob. And let's say that you want to do instant transactions, instant payments, as we had here in all of these channels. And let's say you don't want to pay too much in transaction fees. So the way it can work is that you can have a bunch of different nodes. Let's say these are different people, and some of them can have channels created between each other. So this is, let's say there is a 2-way channel between these 2 people. There is a 2-way channel between these two, and maybe I have a channel like this as well. Now, and let's say I have a channel like this. Now, let's say this is Alice and this is Bob. If Alice wants to pay Bob, instead of paying Bob on chain, what she can do is that she can find a path of channels that goes to Bob. So maybe Alice finds this one here. Let's call her Carol. Let's say Alice finds Carol as an intermediary. And now if Alice wants to pay, let's say 100 Hong Kong dollars to Bob, she can just pay $100 to Carol, and then Carol pays it to Bob. If Alice has a channel to Carol and Carol has a channel to Bob, these are just 2 payments on these channels, and they don't have to go through the blockchain. So Alice can pay Bob using the help of Carol without having to pay transaction fees on the blockchain and without having to wait for confirmations and things like that. So we have instant payments. And yeah, you can basically create like a huge network like this, and then anyone in this network can pay anyone else as long as they can find the path. And this is the idea that is called the Lightning Network. I'm just going to put down the name here so that you can Google it and you can see how it works. It actually needs a lot more cryptography to ensure that the entire process is trustless, because right now, if I'm sending money from Alice to Bob, so as Alice, I'm trusting Carol. I'm sending 100 units to Carol, and I'm trusting that she will send 100 units to Bob. But of course, the nicer question would be, how can I do it so that I don't have to trust Carol? And basically, the idea is that Alice should be able to say, I pay Carol if and only if Carol can prove that she has paid Bob. Okay? But yeah, I'm not going to get into that. That's not really part of the topics of this course. In the next session, we're going to talk about Ethereum and much richer Turing-complete smart contracts. So this is the end of our lectures on Bitcoin at this point. Just Google Lightning Network and find out more about it.